Good morning, Year 12. Today's lesson, we are going to look at how we can approximate definite integration for more complex functions. And the way we're going to look at doing this today is using something called the Trapezium Rule. So we'll come back to this question. I want you to be thinking all the way through how you can explain a good answer to that. Trapezium Rule isn't the only way we can do this, but this is the way that we're going to be looking at today. So on this slide, we've got a picture of a function drawn out graphically. What I'd like you to consider is what feature of the curve would integration help us to find? How could we find an approximate value for this? And how could we then make sure that this approximation was accurate enough? If you need to, pause the video to think about these questions. So thinking through the answers, so integration can help us find the area underneath the curve if we use definite integration and use the limits where we'd like to start and end. You have looked at GCSE finding approximations by splitting the curve up into separate shapes. And trapeziums are a great way of doing this. If we want to make sure our approximation is accurate enough, we need to consider the size of trapeziums that we use. So, for example, if we split it up into 4 trapeziums like that, we'd have quite large areas of errors. So we've got quite a large error here where it's an underestimate. This one's a little bit over, this one's a bit over and a bit under, and this one's quite a lot under. So we've got quite large errors. If we split up into smaller trapeziums, then we'll minimize our errors and we'll have much smaller errors and a much more accurate approximation. There's always a compromise between the two of how long it will take to do the calculations versus how accurate your answer will be. So we're now going to look at how we can come up with a formula to do these calculations for us by splitting a shape into lots of trapeziums. We could just work each one out separately, but actually if we do that, we can simplify the formula down to give us this thing called the Trapezium Rule. We first need to look at a little bit about notation and think about how we can work out the area of a trapezium. So you should know from GCSE, your formula for the area of a trapezium is a half of a plus b times by the height. In our trapeziums, we've set them all up to have the same width, which we're going to call h. Slightly confusingly, we're using h for the width, but each trapezium will have this width of h going all the way through. Okay, we'll put it just in the middle for all the rest of them. The actual a and b values for each trapezium will actually be the y values, because we're starting off at 0 at the bottom and we're taking it up to whatever the y value of the function would read off to be at that point. So for the first one, we'd actually call this one y0. The next one, which would be the value up here, we would call y1. So that would be the value going up here, which is going to be the right-hand side of the blue trapezium, but the left-hand side of the green one. And then we'll use y2, and we'll use y3, y4, y5, and so on. We don't consider exactly how many trapeziums we've got. We can call the last one yn, which would be the nth trapezium. So the one before would be yn take 1. The one before that would be yn take 2. So we're using this subscript notation to denote the different y values. So let's consider each trapezium in turn first, and then consider simplifying. So starting off with the first blue trapezium, so our formula for that one is going to be a half. We would have y0 plus y1, and then we times that one by h. For the next trapezium, so for the green one, so we're going to get a half. This one would have y1 plus y2, and again, we'd use h. For the dark blue, you may be starting to see where this is going. We would have a half y2 plus y3, and then again times by h. And I'm going to skip the middle ones out because they're all going to do something very similar. Let's jump on to the purple one. So the purple one would need half. We'd have yn minus 2 plus yn minus 1 times by h. And then for the black one, right at the end, I might go underneath to make sure it fits. We'd have a half of yn minus 1 plus yn times by h. So if we consider all these, we can actually take out a half h as a factor because that is in every single term that we've got for every trapezium. So then in our brackets, we'd actually have, so from the first one, y0 plus y1. From the second one, y1 plus y2. From the next one, y2 plus y3. And we've missed some of the terms out in the middle. We'd have yn minus 2 plus yn minus 1 plus another yn minus 1 and then plus yn on the end. And then we can actually simplify this a little bit further because you may have spotted something that's going on. So we have the first one, y0 is only in there once, right at the start. The other value that's only in there once is yn, the value from right down here at the end. All of the other y values actually get used twice. You consider the first and second trapeziums. So y1, which is the height up here, is used in the blue one and the green one. y2 is using the green and the dark blue. y3 is using the dark blue and the dark green. y4 is using the dark green and the light blue. All of these other values get used in two trapeziums, the one to the left of the value and the one to the right, all the way up to yn minus 1, which is using the purple and the black. So all of those values get used twice, so we can put that in as a factor in our formula. So we use twice y1 and y2, and we'd use y3 and y4 and however many we need to, all the way up to yn minus 1, the second to last value. So this is our slightly shortened down version of the trapezium rule. We're using the height staying the same all the way through and the different y values. So this is the formula as it's given to you in the formula booklet. They set it up as this approximate integration and they've got all the same terms as we looked at. They also give you a handy little formula over here for working out the h value. N is the number of strips that you use, and B and A, you should be able to see it here as the upper and lower limits. Okay, so this is just considering sharing out equally the difference between the largest and smallest values into that many strips. So it tells you how wide each strip would need to be. So let's take a look at a question we can use the trapezium rule to solve. So we've been asked to use the trapezium rule with 4 strips of 5 ordinates. We'll talk about what this means in a second, to find an approximation to the integral using limits of 5 and 1 for the square root of 3x minus 2 with respect to x. My strong recommendation is you always do a little bit of a rough sketch. I really don't care if it's anything like what the actual function looks like, but we'll sketch something out to try and use it. And we've been asked to do limits between 1 and 5, looking something like this. It's a very rough sketch, and you've been asked to do 4 strips, so that means cut it up into 4 separate strips. So looking something along those lines. This language of 5 ordinates, ordinates is like the word coordinates, it's half a coordinate. So we need to use 5 y values. So we'd have y0 at the start, then we'd have y1, then y2, then y3, and then y4. So to do 4 strips, we actually need to use 5 separate points. And the values we need to use, we need to use 1, we need to use 2, we need to use 3, 4, and 5 will make it work. So our h value, yes, we do get given a formula for it in the formula book, but it should be pretty obvious to you that our h value needs to come out as having a value of 1 to make sure our strips match up with that diagram. So your first job is to put the numbers in the formula. We need to know the y values. We've figured out what x values we're considering. We're considering x is 1, 2, 3, 4, and 5. We need the y values that match. So set yourself up a table, load up table mode in your calculator, and you can calculate the separate values. So if we've got x and then f of x, so we want to use 1, 2, 3, 4, and 5. And then we can use table mode to fill out this table. So a reminder to use table mode on your calculator. First of all, press the menu button. You can then either just press number 9, or you can scroll down through the options until you get into table mode and press equals. And it then asks you what function you'd like to enter. So the one we've just been using is the square root of 3. Use the x button up here. 3x minus 2 is what we'd like to use. You can input a second function at the same time, but we don't need this at the moment. We'd like our table to start at 1, so that's already set up. We'd like it to end at 5, which is the upper limit of our integral, and our h value is 1, so we get up in steps of 1, so that's all fine. Press equals again, and then this has created our table of values that we need to use in the trapezium rule, so we can now write these down. So looking at the values from table mode, we should have 1, 2, 2.646, 3.162, and 3.606. And I've just rounded all of those off to 3 decimal places. Now we've got the values, we can plug them into the formula. So to approximate our integration, so our approximate answer is going to be 1/2. The height value was just 1. Y0 is going to be this value, so 1. Yn from the formula is the final value, so the 3.606. And then we need to use 2 lots of y1, which is 2. So we'll then use y2, which is the 2.646. And our last one would be 3.162. So all the values from our table should be in our formula. They should all only appear in there once. And we can crunch this through in our calculator to come out with an approximate value. So with my calculator, I make that 10.111. Okay, this is only approximate value, so doing it to 3 decimal places probably isn't appropriate. So I'm going to call it a value of 10.1 to 1 decimal place for my approximation to it. What's a great idea also to do on your calculator is to do a quick check. So your calculator actually has an integration function. You can use that to check and get an exact answer. Which comes out to be 10.193. So we can be pretty confident that our approximation of the trapezium was worked correctly. It's actually a very good approximation to the actual integration calculation. So my recommendation for a step-by-step guide: do a rough sketch just to help you figure out what values you need to work out, how many strips you're doing, what x values you'll need to use. That should help you solve all those details. Create a table of values. You can use your calculator table mode. Sometimes it's actually quicker to just keep them exact and keep them as roots. It depends on the particular question. Substitute the numbers into the formula that you can look up in the formula booklet, and then type it in the calculator. I'd recommend just type it all in one go, just make sure you're careful with what you put in the brackets. But do make sure at the end that you check that your answer is sensible using the integration function on the calculator. It should be pretty good, but if you are doing wider strips, you like to get bigger errors, so it may not quite match up. Pause the video here and try these questions. The answers are on the next slide. Make sure that you mark your work. Here is the second example, just to give you one extra point. So we've been asked again to use the Trapezium rule, this time with 5 ordinates, to find an approximation for the area between x equals 0, x equals 2 pi over 3, slightly unusual coordinate that we'll get to, and the x-axis, and the curve y equals the square root of cos of a half x. So the question's phrased in a different way. It's talking about area rather than talking about integration, but we know that integration and area are linked, so that's what it's liking us to do. It's given us limits to use of 0 and 2 pi over 3 for our integration. So what they actually would like us to do is calculate an approximation to the integral between 0 and 2 pi over 3 for the function which is the square root of cos of half x with respect to x. So this is what they'd like us to do. So it is using our Trapezium rule in the same way as before, but the question's phrased in a different way. There is one really important thing in here to bear in mind, and this unusual x coordinate is a link to that. We need to actually work in something called radians mode on your calculator to do this. So here's a quick demo on how that works. So to turn your calculator into radians mode, you need to press the shift and then the menu button to go up into the setup. Number 2 says angle unit, and then you get a choice between degrees, radians and gradients. So your calculator is probably set up into degrees mode. We can press number 2 to turn it into radians mode. And you should notice up here that you have a little R where you used to have a little D. So any calculations we now do will work in radians mode, and we need to use this a lot in year 13 for any time we do any kind of calculus with trigonometry involved. So if we now have a go at running through the question using the Trapezium rule, so following the steps, first idea is to do a bit of a rough sketch of what's going on. Again, I'm not really considering at all what this curve is going to look like. It's a trig curve, it probably goes up and down a bit. I've been asked to do between 0 and 2 pi over 3. I don't really mind what it looks like. We've been asked to use 5 ordinates in the question. Remember, 5 ordinates means the same thing as 4 strips. So we need to cut it in half. We need to cut that one in half, and we need to cut that one in half. Okay, if we think about cutting these in half, if this is 2 pi over 3, so half of that would be 2 pi over 6. Okay, so our equal sections that we're actually going up in, so this would be 1 pi over 6. So we're going up pi over 6, then 2 pi over 6, then we'd get 3 pi over 6. And then 2 pi over 3 would be 4 pi over 6. So our h value that we're using is pi over 6. So we can now switch to table mode, and we can put these numbers through to complete our table of values. We've got our x values and we've got our f of x values. So if we set our table up, and then we can use table mode to complete it. So we need to use the 5 ordinates, we need to use 0. I'm going to call it pi over 6. I could simplify the fractions, but for the ease of spotting what h is, 2 pi over 6, 3 pi over 6, and 4 pi over 6. So they're the fractions that we're going to use, and table mode will do the rest for us. So again, I've got my calculator in radians mode. I've entered the function in. You can just type the limits in using pi on the calculator and it will turn them into decimal values for you. So mine comes out as being 1, 0.983, 0.930, 0.841 and 0.707. Actually, just checking carefully, that one should be 0.931 rounded to 3 decimal places. Okay, if you are asked for an appropriate degree of accuracy in your answer, you should always make sure your separate parts have a higher degree of accuracy than what you've been asked to give. So because I've done these to 3 decimal places, probably 1 decimal place or maybe 2 we could get away with would be suitable for our approximation. So if we now substitute our values in to work out our approximate integral, so we need a half of h was pi over 6. We need y0, which is 1, plus yn, which is 0.707. And then we want 2 lots of all the middle terms, 0.983, 0.931, and 0.841. Important you put the double set of brackets into close at the end. So enter that into your calculator, and my answer comes out as being 1.889. So if I round that off to 1 decimal place, I'm coming out with 1.9 to 1 decimal place. Again, use the integration mode on your calculator to do a quick check to make sure this seems sensible. So if I tap that through in the integration mode, my calculator is coming out with 1.896. So again, we've got a pretty good approximation there. It looks like we can be confident we've run through our trapezium rule correctly. Only other little bits to consider. You may be asked to consider if your approximation is too big or too small. This does rely on you being able to sketch the curve more accurately than we've been doing so far. So for these 2 pictures here, one of them will be too big, the other one will be too small. So if we consider, the easiest option is just draw one really big trapezium and see what happens. So for this one, we would end up with our trapezium being too small. All of this bit here is getting missed out. We'd have an underestimate for what the actual value was. If we do the same with the curve that's curving the other way, the curve facing upwards, our trapezium would go above the curve. So this bit here would be our error, and we would get a value that was too big. Even if we split up into smaller trapeziums, we'd still get this same pattern going on. So it's easiest to explain with one big trapezium. So the one on the left, where the curve is facing downwards, you get an underestimate. The one on the right, where it's curved upwards, that will give us an overestimate. How can we make our estimate better? So we've just talked about if you do one big trapezium like this, we will have quite a large error in this place here. If we split it up into more trapeziums, then each individual one should have a small error, and we should overall get a more accurate result to it. So in this one, that's only given us a very small error. That one's even smaller. A bit of an error on this first bit, but overall, these 3 little bits here, here, and here are nowhere near as big as the error in the first problem. So to make our estimate better, all we need to do is use more strips. Okay, if you want to pause the video here, here's an exam style question that you could try. Here is the mark scheme solution. So wrapping things up, so think back to the learning inquiry question we had at the start. How can we approximate definite integrals for complex functions? You should have a pretty good idea how we can do that now. Think about explaining how that can be done. Don't just say, we just use the trapezium rule. Why do we use it? Why does that work? We've only done one method today. There are others. For those of you studying further maths, you will look at some of these in more detail as we go through. So we looked at trapeziums. Could we have used different shapes instead? What other options are there? If you'd like to do a bit of research into that, that'd be a nice place to do it. And actually, just think about why this is a really important method. So from looking at the functions today, there are lots of things that we don't know how to integrate. So if we don't know how to integrate something, we can still get an approach or an answer that's very similar using this numerical method instead. Actually, in the grand scheme of things, we only know how to integrate very few functions. We're going to add more of those things in the second year of maths, but there are still things out there that we wouldn't be able to easily integrate. We can use a numerical method like this instead. And we've been using the calculator to check, but it will be using a numerical method like this to do its approximations for us. It will just be able to compute lots of strips very quickly with very accurate answers. Okay, thank you for listening. Make sure you complete any follow-up tasks set.